impact motion, impact energy, then I die. Okay, you control, you control under the load, right? So likewise, at point B, it can move, yes or no? At point B, it can move. Yeah, it will not break at that. At point A, where you don't allow motion. Okay. Now, what I've just taught you is how to do failure analysis. Okay. Okay. Now we know where is tensile, where is compression. Okay? So when we know when is tensile, when is compression, okay, we don't really need to care about whether y is positive or y is negative anymore, is it? Right? So we can just easily apply that. We know that stress x is equal to my mz over izz multiplied by y. Right? So what you realize here is the negative sign gone missing. You might, he was talking about negative sign. Now it go. Why we can take away the negative sign? Why? Is this reason? We already applied the sign already. We know down here is what? Tensile. Down here is compression. If I call this point over here, the top point, I call it alpha. The point that down here is known as beta, right? We know that point alpha is going to be under tension, point beta is under compression, right? Based on the moment vector and based on what? The deformation, right? We are doing this based on deformation, right? We drew the deformation pattern and we know what, which one is tensile, which one is what? Compression. We know that. That's why now the formula is just, okay, stress x is equal to mzy over izz, because we know what is tensile, what is compression. Okay. That's why I'm trying to train you guys, not just plugging everything into the black box. I want you to see physically what is going on. Okay. Because in later times you will forget, is there a minus sign or no minus sign? Right? You will forget, I will forget, right? So by looking at a deformation pattern, you'll know what is a tension and whether is it under compression. Okay. Now, so the next thing that we're going to do now, okay, which I'm going to teach you now, is when is it a width and when is it a depth. Okay. So let's look at cross-sectional view now. Okay. So we are going to look at cross-sectional view.
Sir, is there supposed to be a minus before that moment or no?
I told you already. We're going to take it out.
Okay.
Right? Why we take it out? I already said earlier, because we know when is it a tension, when is it a compression already, right, Justin? Okay. So let's say that this is 10 years later. You are a certified engineer, you are a chief engineer, and you realize, I can't remember, is there a plus or minus sign in front? And you don't have textbook with you. What are you going to do? No internet. Okay. No internet. What are you going to do? Right? So you will physically see how the structure deform, and you know whether is it tension and compression. That's what good engineers is. Okay, you have to feel what you calculate, is it good or bad. Okay. Now let's do a
But we
cross
have
section.
to mention where, but we have to mention where it's tension and where it's compression.
Yes. Okay. So over here, based on analysis. So this is the part of analysis, right? Based on the moment vectors that you can see over here, right? This is in compression and this is in tensile. And why is that? Remember I wrote earlier, the head of the moment vector is always what? Compression. The tail end of the moment vector is always under what? Tensile. Always. Okay. Now let's look at the cross-sectional view now. So we're going to look at the cross-sectional. So now I'm going to view, yeah, this now. So this is my y.
Sir, we can't hear anything. You muted yourself.
How long was I muted? Any idea?
Like a minute, maybe?
Oh, so you cannot hear.
Yeah,
Okay,
about a minute, 30 seconds.
okay, so let me know. Okay, next time if you all cannot hear me, let me know. You can see my mouth moving, nothing. Let me know. Okay, so I'll repeat it. So the cross-sectional view, right? So we are doing the cross-sectional view now. So what we are trying to do is we are trying to identify how to find IZZ. Okay, so IZZ, this is our ZZ. Okay, this is our ZZ axis. Okay, so we know that IZZ is equal to width multiply by depth power of 3 divided by 12. Or in short, is BD cubed over 12. Okay, now you guys are very familiar with this already. But when is it a width and when is it a depth? I think I touched this on the shearing stress before, but I want to do it again. Okay, so any geometry that is parallel to the z-axis, so this is parallel to the ZZ axis, yes or no? Right? This will be always known as the width, or in this case, W. Okay, so I'll write down the geometry parallel to the axis, to the z-axis. For this case, YZ axis, because we want to find IZZ, okay, it's always the width. Okay, and then any geometry. So if you look at this geometry over here, this geometry is what? If I extend the ZZ axis, this geometry is what? Perpendicular. Okay, so the geometry perpendicular to the Z axis, right, is always the depth, right? So for this case, we can calculate IZZ. The width is always 12. The depth is 20. Power 3 divided by 12. So this will be equal to calculator. So this will be equal to 12 times by 20 power 3 divided by 12 times by 20 power 3 divided by 12. So it's 8 times 10 to the power 3 millimeter 4, or 8 times 10 to the power minus 9 meter 4. Okay, so that is our IZZ. So from here we know, okay, so let's say now we want to calculate stress in the x direction. Okay, stress in the x direction. So based on the geometry that we have, right, we know that this is our y direction. Okay, that is our y, right? We no need to bother whether is it y positive or y negative now, because we know tension and compression. Where is tension, where is compression? Okay, so now we know y. So if the formula that we're going to apply is equal to mz over IZZY, and the question want us to calculate what? The stress max, right? We're going to calculate the stress max. So when that's the case, y for our in our context, y will be equal to 10 millimeters, or 20 divided by 2, right? Because it's from the neutral axis. Okay, so 20 divided by 2, this is equal to 10 millimeters or, right, 0.01 meter. Okay, so let me sketch out the points again. Okay, so let me sketch out the points. Where is my cursor now? Okay, so I'm going to call the top part. Okay, did we call the top part alpha and the bottom part beta? Yep. Okay, so we're going to call this point alpha, this point beta. Okay, right? So we know alpha is in what? Tensile. We knew that already. And beta is in what? Compression. That is so weird when hold on. There's something wrong. Okay, hold on. So this is in tensile. That is in compression. Okay. So because we already analyzed it already, right? We know alpha is in tension. That's why you can ignore initially what we talk about where you need to use what stress x equal to minus my, right? You don't need that anymore, right? You use the moment vector to find that already. Okay. So now we know that stress x we're going to find at alpha. So this will be equal to, so the moment is 60 multiplied by 0.01 divided by 8 times 10 to the power minus 9. Right? So 60 multiplied by 0.1 divided by 8 power minus 9 is equal to 75 times 10 to the power 6 Pascal tensile. Okay, so the other one, stress X in beta, you already declared it's under what? Compression. So you know that you just put a minus sign in front. So this is equal to minus 75 times 10 to the power 6 Pascal. Okay. So this is A. Okay. Now let's now we do B. Okay, we do B. Okay. So I'm going to do it side by side so you can see the difference. Okay. Why will it always be the same? Phuket, what do you mean will it always be the same? How do you mean? Phuket.
The values, sir. Both of the values.
For this case, it happened to be the same because the structure is axis symmetry about the Z and the Y axis.
So if the part is not symmetry, only Y value is different?
If the part is not symmetry, yeah, then later on, okay, I'll show you an example when it's not symmetry. Okay, later on, when it's not symmetry, then the values will not be the same. Okay. Right. So now, the next thing that we're going to do now, okay, I'm going to now do part B now. Okay, so let me get you a view that you can see what I'm writing now. Okay, so we're going to do part B now. So this is side by side, you can compare. So part B, right? Okay, so I'm going to write part B now. So when we look at part B now the moment is acting about where? Part B, now the moment is on the y-axis and is going to go at 60 Newton meter. Okay. So now stress, we are still finding stress in the x direction, by the way. Okay, we are still finding stress in the x direction. So stress in the x direction is equal to my over Iyy multiplied by z now. You see the difference now, right? When is z is mz over izz multiplied by y. But when it's in y now it's my over Iyy multiplied by z. Again, by right, I should put a minus sign down here, but I don't want you all to worry about the minus sign. Or don't worry about the sign, because once you look at the deformation, you know whether is it positive or negative. Okay, so don't worry about the sign. Okay, so I'll write down here